All right, hello everybody. This is Professor Iris Miano coming at you with a relatively brief lecture video on how to solve absolute value inequalities. Okay, so we already had a discussion in lecture video regarding how to solve absolute value equations. So the rules are going to be a little different in order to solve inequalities, as it often is with inequalities. They're just, it's a whole different animal, and we need to make sure we understand what the procedures are depending on what kind of structures we are given. So let's jump right in. These are basically your rules that you want to follow in order to solve various different styles of absolute value inequalities. So in each case, you're only going to move forward with the evaluation of an absolute value inequality if the absolute value is either less than or equal to, greater than or equal to a positive number. That means that if you have an inequality in which an absolute value is being compared to a negative number, you just stop right there and you just say that there's no solution, since your absolute value is not going to be comparable to a negative number. Remember, absolute values are representing distances away from zero on the number line. That is the literal definition of an absolute value. So if your A value that you're dealing with here from the get-go on an inequality that you're set to solve is equal to a negative number, or if you perform an operation to isolate an absolute value expression and then the number on the other side of the inequality becomes negative, you just stop right there and say no solution. But if A is a positive number, then these are all of the different ways that you evaluate an absolute value in the context of an inequality. So the way I think about the rule is this: if your absolute value is less than or equal to, right? So if absolute value is less than, then you set it up as a compound inequality, okay? In which the expression inside of the absolute value, in this case we're just generically calling it u, it's just u as any algebraic expression, gets thrown in the middle of a compound inequality in which the A value's original value is the upper bound, right here where my cursor is hovering, and its opposite is the lower bound. And so it's the same rule whether you have a less than or a less than or equal to. You just make sure that those symbols come along for the ride in their transition into a compound inequality, okay? And this is because when you have this situation, it's analogous to having two individual inequalities with the word and in between, but anytime you have two individual inequalities and the connective for them is the and word, you could just write it more concisely as a compound inequality, which is what we have here. But when we go over to the other case, what if your absolute value expression is greater than that positive value A, or greater than or equal to, right? So these last two cases are pretty much synonymous. It's just the only difference is that one is a strict inequality and one's inclusive, okay? But if your absolute value is greater than the positive value A, or greater than or equal to, then you need to set it up into two separate cases of individual inequalities with the connective or in between. Now, why do you have to do it this way? Because you're dealing with a different relationship here. When your absolute value is greater than some positive value, it's an or situation. Okay, anyway, but what is the structure by which you separate the two cases? Well, your first case is going to be taking that u value, whatever's inside the absolute value bars, and you're going to set it less than the opposite of your original value A. That's case one, you can say, or one of the cases. And then the other case has to be, again, take whatever is the expression inside of the absolute value bars and then set it greater than the original value A, okay? And if you have a greater than or equal to situation, comparing your absolute value expression to that positive number, then you just put those bars underneath, but it has exactly the same structure, and you have the word or in between. Now, when the difference between these two main cases graphically, like if you have a compound inequality versus two singular inequalities that are connected by or, this is always going to be giving you some sort of enclosed endpoints and all the space in between graphical representation, whereas these are going to be two disjoint sets that we're going to unify. So we'll cross that bridge when we get there. I mean, we'll see it right away with the examples that we're going to cover, and that's what we're going to drop right into next. So if you are looking at these structures and you're just like, oh God, how am I going to remember all this stuff? Well, if you're using the lecture notes that I provide that go along with this lecture video, they are at the top of the first page for you to reference while you're working on these examples with me. So we're going to start off real super simple for the first two examples, and then we're going to get a little crazier and crazier as we go, and then that last example is going to be like, whoo doggies, it's going to be the craziest one of them all. But don't worry, we're going to get through it together, okay? Here we go. Let's start with the absolute value of x is less than 9. Okay, so we're going to solve the absolute value inequality, which for this one is just going to be simply implementing the rule being this first one, right? Absolute value of what x is less than 9, where u equals x and a equals 9. Is that what we have? It sure is. So we're going to implement this compound inequality, replacing u with x and a with 9. You'll see in just a second, okay? And that'll be solving the absolute value inequality. And then there's more instructions after that. Once you've figured out the solution, you want to express it in set builder notation and interval notation. I'm going to show you how we can capture both of those from the solution. And also we're going to graph the solution set. Now we're not going to do these items in exactly the order that they're presented as you read these instructions, you know, in the sentences in order. We're actually going to solve first, then express the answer in set builder notation, then we're going to graph it, and from the graph I feel like it's easiest to glean the interval notation solution set. Okay, cool. So first, solving this inequality, because it's so simple and we don't have any kind of a complex expression inside of the absolute value bars, we can go straight to implementing the rule. Okay, the absolute value is already isolated, and it's you know, the number that we're comparing it to is positive, right? So we know that we have something to do. So here is implementing that rule, in which, according to the general rule on the previous slide, the u is equal to the x, so that's the value in between, and then the positive number a is 9, so x is going to be faceted inside of a compound inequality where the upper bound is that same value a, which in this case is 9, and the lower bound is its opposite, okay? So that's the solution. You could check this off your list. We solved the absolute value inequality. First item is done. Next, we're going to express your answer in set builder notation, okay? What is set builder notation? That's the curly brackets, and you create a set, and it reads something to the effect of the set of all, in this case, x, such that, and then we're just going to simply copy down this compound inequality and then close it up with another curly bracket, like so, okay? And again, this set of symbols reads as the set of all x such that x is between -9 and 9 exclusively is one way that you could read this. If I had the equal to options here, I would say that x is between 9 and -9 inclusively, indicating that I'm including the endpoints as part of the solution set. But since we have a strict inequality on either side of our compound inequality here, we would say that x is between 9 and -9 exclusively. Okay, great. So that's the set builder notation. This second thing right here, express your answer in set builder notation, check. We're going to hold off on interval notation for a moment. what I want to do next is actually graph the solution set, okay? So I'm going to use the solution, and, you know, as it appears in the set builder notation as well. I guess this is where I'm going to focus. And I'm going to have -9 and 9 get graphed on this number line, okay? But I'm going to do it in a very specific way. So you probably maybe ever graphed points on a number line using open dots or closed dots, and you can still do this here. But another set of notation that lends itself nicely to the interval notation, which we're going to get to last, is to use parentheses on bounds that do not include the endpoints like we have here because we have strict inequalities, or brackets to indicate that we are plotting points that include the points themselves as part of the solution set. So since we have strict inequalities on this compound inequality here for our solution set, we're going to put parentheses at -9 and 9 facing one another. So I've gone ahead and lit them up in orange so that hopefully they look really bright against the purple graph there. And I also have my endpoints lit up in orange here. So this is just plotting the boundary points in using appropriate notation. And a parenthesis on a graph is synonymous to an open dot on a graph, okay? But again, I'm going for parentheses or brackets on my graph because I'm going to use that same notation in the interval notation part of my solution, okay? Great. So here are the endpoints as they pertain to the compound inequality. Here are the endpoints on the graph. But I also want to color everything in between to indicate the entirety of this compound inequalities, like all of the values that are being represented. It's everything in between the parentheses as well. So notice that I've colored in the number line orange. You know, that was just a stylistic choice there. You can color it in with pencil or whatever color you have available to you if you're going to be physically practicing this. And just, yeah, fill in the entirety of the line that is captured between the upper bound of 9 and the lower bound of -9. And again, the parentheses are indicating that those bounds are not part of the solution set. And so what you'll do is you'll take your parentheses, you'll take the upper and lower bounds, you'll put a comma in between them, and that gives you your interval notation solution, okay? There we go. So hopefully everyone can see how graphing at first might lend itself nicely to illuminating what the interval notation looks like too. And that'll do it. Again, just to be clear, we have covered all of the bases in this instructions here. We've solved the absolute value inequality. That's this bit right here that was a one-stepper to solve it. We're going to have more examples where it's multiple steps, but it was just the one step. That's the solution. Here I am expressing the solution using set builder notation. Here's the solution using interval notation. And then here, of course, is the graph. Okay? Great. Let's move on to our next example. Now notice that we will be having our absolute value expression greater than or equal to, but greater than. The direction of the symbol has changed. So the way that you evaluate the absolute value is different. You're going to use the or with the two cases for two individual inequalities, okay? So here's how it'll look. You're going to take your x value and set it less than or equal to -4, or take your x value and have it be greater than or equal to 4. So it's basically like just drop the absolute value bars and that gives you one of the cases, and then flip it and, you know, reverse it kind of for the other case, if that makes sense. You flip the direction of the inequality and put the opposite of that original value that you're comparing the absolute value to in the inequality. Okay, and that's, you know, it as far as the solution is concerned, because we had a relatively simple inequality. The expression inside the absolute value was just simply the variable x. So that's your solution set. Check that first thing off your list. We found this, we solved the absolute value inequality, done. Now let's express your answer in set builder notation, okay? Literally, you just take this, the two individual absolute value statements and the word or in between, and throw it in set builder notation, okay? And this will read x, this is the set of all values x, such that x is simultaneously less than or equal to -4, or x could be greater than or equal to 4. Okay, so we're going to have two disjoint sets here, and we want to graph them. So take these individual inequalities one at a time and graph them on the number line. Yes, we're going to skip the interval notation step for now and graph first, because I feel like the graph using parentheses or brackets on your endpoints, and then, you know, coloring in all of the values that make up the solution set that satisfy the inequalities is nicely lending itself to determining the corresponding interval notation. Okay, so let's focus on x is less than or equal to -4. X is less than or equal to -4. Okay, so the equal to option means that the endpoint of -4 is going to have a bracket on it. But which way should the bracket be facing? Should it be facing this way to go off into negative infinity, or should it be facing this way to go on to positive infinity, right? Like, which direction are we going to be going? We'll read it out loud one more time. X is less than -4. So that means we're going to be capturing -4 and everything less than that. And if you're trying to determine or represent something less than a value on the number line, you're going to be moving to the left, right? Just like Beyonce was telling us, to the left, right? She was kicking out her less than amazing boyfriend, and that's what the song was about, less than. Just kidding. It wasn't about number lines or graphing at all, but that's the way that I remember moving to the left, representing on a number line. You are becoming less than a previous number, or you're subtracting. You know, you could think of it in a couple different ways. Anywho, let's go ahead and put that bracket down at -4, and we're going to have it facing the direction moving to the left. And so here, yeah, I'm representing that endpoint of -4. And because of the correct choice of representing it as a bracket, I'm including that endpoint, and then I want to capture everything to the left of it. And notice that, like, if you think of the inequality symbol as an arrow that's pointing, like, what direction is it pointing? It's pointing this way, right? So that's another way that you can kind of match these things up, but only if your inequality reads x with the inequality symbol and then the number. If you have the x and the number switch positions, then you really can't use that rule, okay? Or that, connection. Okay, so then this bracket and this colored in line represent this part of the two cases inequality, right? And so where is this line going? Like, does it go on forever and ever and ever in to negative infinity? Well, sure it does. Okay, so we'll get to that in just a minute. Actually, put a pin in this, and let's go ahead and represent the other inequality. Okay, so it reads as x is greater than or equal to 4. So that means 4 is another endpoint that we need to consider. We should have the bracket in place because we have the equal to option, and it should be facing in the other direction. Why is that? Because I'm going to grab everything greater than 4. Literally, this says, let's read it again together, x is greater than or equal to 4. So have the equal to option represented with the bracket, and then color everything greater than 4, including the arrow point, which indicates going off to positive infinity on the number line. Okay, so like I said, those arrow points are representing something very specific that we want to capture in regard to coming up with the interval notation. So for this example only, I've written down negative infinity here and infinity there. It's not wrong to represent that on your number line in the future, but I didn't provide that on your lecture notes or anything, but you could certainly add it. And I think it's really nice to add it, especially in regard to coming up with the interval notation for this one, which is kind of tricky because there's two separate disjoint sets that we need to unify. And I'm using this term unify very purposefully because there's a symbol that kind of looks like a U, which represents the unification of two sets. So here we go. This is how we will represent the solution set in interval notation. So notice that we are unifying, that's this U symbol right here, the set of all values going all the way down, like from negative infinity, so off into infinitum in this negative direction, but going all the way up to -4 and then stopping but including that endpoint. That's what the bracket is indicating here in the interval notation and also in the graph right here. Similarly, but different, we have a lower bound of 4 that we want to capture, and then everything up until positive infinity needs to be grabbed, and so that's why we have 4 comma positive infinity on the other side of the union. Another thing I want to point out is that whenever you have these two disjoint sets and they go off into negative infinity and positive infinity on one or one or the other side, then you will need to encapsulate positive and negative infinity with parentheses. And why is that? Because there's no hard boundary on infinity or negative infinity. So the most appropriate, what's the word I'm looking for? The most appropriate notation is going to be a parenthesis in this case. And that's it. We did the things. We solved it. And by it, I mean the absolute value inequality. We solved it here. We put the solution set in using set builder notation here. We have interval notation solution there, and then we graphed it. So we covered all the bases, and we're ready to move on to the next example. Okay, so notice that we do have an absolute value expression on the left-hand side of the inequality and some stuff outside of it, okay? And then it's being set less than or equal to some positive number. That's all well and good, but we need to perform some algebra on this inequality in order to isolate the absolute value expression. So the first thing that we're going to do in order to isolate the absolute value of x minus 2 is we're going to subtract 2 from both sides. So I've indicated that just in red here, and then I'm going to off into the middle of the screen put the result of subtracting 2 from both sides, okay? And then at this point, I'm going to recognize that, okay, I have an absolute value expression and it's less than or equal to some positive number. So what's the rule? Go back to, the front, the first page at the very top of your lecture notes if you're using them, and figure out which rule is best to evaluate this absolute value portion of the inequality. Well, we're going to have a compound inequality, right? In which we have the expression inside the absolute value, which in this case is the entirety of the binomial x minus 2, is going to be between -1, so the opposite of that bound, 1, and +1. Okay, so we're going to have the opposite of the original number and the original number as the lower and upper bound respectively on a compound inequality in which the central section consists of the expression inside the absolute value. Now we're going to need to solve for x in the middle, which in this case will include adding 2 to all sides. And why am I saying all sides? Well, I'm saying all because there's more than 2 sides of a compound inequality. There's actually 3 different sides. So we need to add 2 to all sides. So here I'm adding 2 everywhere needed, and it's going to eliminate, right, the subtracted off 2 here, and then the lower bound will then become -1 and the upper bound will become 3, like so. Okay, now what we've done is we solved the absolute value inequality. There's no other what's it called? There's no other simplification that's possible. So now we're going to, I would say, graph it first, and then we'll do the interval notation. That's the order in which I like to do things. Certainly, if you can easily look at this compound inequality and go straight to interval notation, by all means do so. But I like to graph it first. So I'm going to start with the plopping down brackets on the upper and lower bounds of 1 and 3 respectively. Brackets because I have the equal to option in my compound inequality. So, oh sorry, I got ahead of myself there. What we really need to do, I guess if we're going to go in order, is to express the answer in set builder notation. So that's just take your compound inequality and plop it inside of some curly brackets with an x and a vertical bar. So this will read the set of all x such that x is between 1 and 3 inclusively, because we're including the endpoints. That's what these little horizontal lines underneath the inequality symbols indicate. Now we're ready to graph, if I'm not mistaken. Let's go ahead and put 1 and 3 down with brackets facing one another, okay? and let's color and everything in between to indicate the entire inequalities graph. Okay, cool. So then it might be easy to see how you write the interval notation, which will literally be this bracket with a 1 next to it, then a comma, 3, and then this other bracket there, like so. Okay, and that's it. That's all there is to it for example C. All right, moving on to example D. Here we go. We've got, all right, another inequality, absolute value inequality, but the absolute value is yet to be isolated. So let's do the thing that we know we need to do. We need to add 1 to both sides of the inequality, okay? And then notice that the absolute value expression is greater than some positive numbers. So this is when we need to break it up into the 2 cases in which the expression is set less than the opposite of the original value. There's also, you have to put or in between the other case in which the absolute value expression is greater than that positive value. In this case, it's 3. We will simultaneously solve both of these individual inequalities, which in this case will amount to adding 5 to both sides of each individual inequality. So let's go ahead and do that. We could do it all at the same time if we like. And these are the resulting inequalities that we will get. And we need to plot both of them on the same number line. And then note the interval notation, of course, after we do the easy thing, which is once you've solved your absolute value inequality, which is what we've done at this point. Both of those individual absolute value both of those individual inequalities cannot be simplified any further. So here's the solution. Here's the solution set represented with set builder notation. You just simply plop these 2 individual inequalities as you see them with the word or in between as well, between some curly brackets with an X and a vertical bar. So this set notation can read as the set of all X values such that X is less than 2 or X is greater than 8. There you go. Now, let's go ahead and graph these individual inequalities one at a time. I'm going to start with X is less than 2. Now, we have a strict inequality, a less than symbol, no equal to option, so we're going to go with a parenthesis at 2, and since I'm less than, everything is going to be less than 2, my parenthesis is going to be facing this way, and I'm going to grab everything below it. So there's my parenthesis, there's me grabbing everything below it. And I am coloring in the entirety of the number line, including the arrow point, which points off into negative infinity. Okay, so that's that side of it. The other side of it is going to have an endpoint at 8. Again, a parenthesis is appropriate. I'm going to face it this way so I can grab everything going off into positive infinity. Okay, so feel free to add infinity symbols here and negative infinity here in order to effectively capture the interval notation version of the solution, and don't forget your union symbol in between. And yes, we are having parentheses encapsulating negative infinity and positive infinity because that's convention, right? You always have parentheses there, but the parentheses are surrounding the 2 and the 8 endpoints specifically because we do not have the equal to option here. We have strict inequalities and the parentheses represent that. Okay, great. I believe I have 2 more examples. Let's go ahead and just dive into the next one here. All right, so its structure is very similar to the previous 2 that we've just gone over. We recognize that we have an absolute value expression inside of our inequality. So the first thing we need to do is isolate that absolute value. So the first step here is going to be subtracting 7 from both sides, and we will get this. All right, now the first thing you might be noticing is which direction is this inequality facing, because that'll determine if you're going to be, evaluating the absolute value with either a compound inequality or 2 individual inequalities with the word or. But wait, hold on. This absolute value is being compared to a negative number. Uh-oh. Bells and whistles should be going off in our heads because an absolute value cannot take on a negative value. So that means this absolute value, there's no way it's going to be less than a negative 5. It's not going to go further negative beyond negative 5. It can't even be equal to negative 5, right? So whenever this occurs, we just go ahead and stop working and conclude that there's no solution. So you could write no solution, just in English like so, and here are the two different symbolic ways that you can represent no solution. Curly brackets with nothing inside, that represents the empty set, and so does this 0 with a slashy through it. And then don't graph anything because there's nothing to graph. There is no solution to represent graphically or otherwise. Okay? And that's it for that one. That was quick and easy because we recognized that there was nothing to do at the appropriate step. Great. Here is the last example, and it is by far the most challenging, but we can do this, okay? So notice a couple of things right off the bat. The inequality has the absolute value portion of itself already isolated, but there's a variable on the right-hand side. Is that okay? Sure, it's okay for us to do. We just need to treat the binomial of x plus 2 as like that a value, okay? As long as we do that, we just kind of structurally treat it as some positive number, then we're going to be in good shape. So notice that the absolute value expression is greater than or equal to. So in that case, we've got to break it up into the two cases. And the two cases are, take everything inside of the absolute value and set it less than or equal to the opposite of the value on the other side of the absolute value, which in this case is the binomial factor x plus 10. So notice that I put the entire binomial factor of x plus 10 inside of some parentheses, and I'm negating it, and I'm going to evaluate the distribution of that negation in a separate step. And then of course there's the other case in which you take the inside of the absolute value expression that is, and you just set it greater than or equal to the original value that it's being compared to. Basically, it's just the original inequality, but with the absolute value bars dropped, okay? Then we're going to do one simplifying step here on this first case, basically distributing through that negative sign, and then we're going to perform the steps that solve both of these individual inequalities simultaneously. So for this case on the left-hand side, we're going to start by adding 3x to both sides. I'm actually going to do the same thing over here as well, mostly because I want the variable part to have a positive coefficient, so I don't have to ever multiply or divide both sides of the inequality by a negative number, because I'm going to have to remember to switch the direction of the inequality if I have to do that. So I'm just going to avoid having to do that by adding 3x to both sides of both inequalities, okay? And here will be the result of that. So, it gets eliminated here. This becomes a positive 2x, and then now the other components come along for the ride for the first case, and then for the second case, of course, this gets eliminated as desired, and then we have the x on the other side, the collection of them being 4x's. Okay, so now the steps that solve the individual inequalities are going to be different, but similar from now on. So on the left-hand side case, I need to add 10 to both sides. That would be the next most efficient step, whereas the right-hand side case, I should be subtracting 10 from both sides. So here's what that looks like with my little color-coded bits. Whenever I'm adding two things to both sides in this lecture video, I do it in blue, and I'm subtracting something from both sides and doing it in red, just for, for fun. Here's the result of those operations, and then on the left-hand side case, we're going to divide both sides by 2, oh no, that's a typo. Hold on, let me actually just fix that real quick. Yikes, that became a 4 right here. There. Sorry about that. And then it's going to be a typo for the remainder. Fixing it in real time. Oh boy. What I really should do is just pause the video and take care of this, but I'm going to go ahead and just fix it with you guys watching. All right, hold on. We're almost there. Terrible. But oh well. That's what happens sometimes when you make an error. Almost there, guys. So you're kind of seeing the background of what's happening. Spoiler alert. This is what's going to go down. All right. Oh, one more time, and then let's go back to where we were with it. Okay. Where were we? Okay, so the error occurred right about there. Okay. back to the slideshow. Thank you for your patience. Okay. So we subtracted 10 from both sides, and we get negative 8 is greater than or equal to 4x. Okay, we're good to go. Then it'll be dividing both sides by 2 on the left-hand side case, and the right-hand side case we should divide both sides by 4. Why? Because, you know, the coefficient for the x is a 4 over here. We're just trying to get rid of those coefficients and get x's isolated, you know, in both cases it's on the right side, which is a little funny as far as like reading this inequality. 6 is less than or equal to x. Don't we usually read our inequalities as x is being compared to some number, you know, reading it from left to right? Yeah, well, that is normal, and that is something that we have relied on in order to do our graphing step. So what I might suggest that we do in this case, and this is a good rule of thumb just in general, if you want to flip over an inequality, you got to do what I call a pancake flip, which, you know, visualize if you've ever made pancakes in your life. What do? You put the spatula underneath your pancake, and then you flip it over. So what was the left side of the pancake becomes the right side of the pancake, right? It's just like, you know, the sides of the pancake get flipped in regard to that. So I don't have a visual to have in this video here, but I'm hoping that that description of an action is kind of synonymous to what you see here. So let's pancake flip both of these. So for this first one, the 6 and the x are going to switch places, but so does the direction of the inequality. It needs to flip over. Similarly, the negative 2 and the x are going to switch places, and then the inequality is going to go from greater than or equal to less than or equal to. Okay, so here is what the flip looks like, okay? The position of the items flip, the direction of the inequality flips for both. Then it reads nicely and aesthetically and conventionally, and I think it's a little bit easier to determine how to graph from here, although we are going to do an intermediate step of expressing your answer in set builder notation now that we have the solution set. Okay, so we've solved the absolute value inequality. Check that off your list. X is greater than or equal to 6, or x is less than or equal to negative 2. So we will be plotting two disjoint sets and unifying them in order to represent the interval notation, but hold on. We have everything we need to plop down the set builder notation, which again is just take these two individual inequalities with the word or, put them inside some curly brackets, some braces with an x and a vertical line. And I'll again read to you how this goes down. This is the set of all x such that x is greater than or equal to 6, or x is less than or equal to negative 2. Okay, so let's individually graph these two inequalities on the same number line, and then we will from there glean the interval notation version of the solution set. Okay, cool. So let's start with x is greater than or equal to 6. So we have a bound on 6. It's including that endpoint of 6, so it should be a bracket, and I'm facing it in this direction because I want to grab everything bigger. Everything x is greater than or equal to 6. So I want to face to the right and grab everything that's to the right of 6, all the way up to the to positive infinity. So color in the arrow point, which that just indicates the number line, the idea that the number line is going to positive infinity. Okay. Similarly, we have another bound at negative 2. I want to have it be a bracket and face it traveling from there to negative infinity because I am less than or equal to negative 2 as well. Okay, so unify those two sets. I am starting from the depths of negative infinity going all the way up to negative 2 and including the endpoint, and then I'm going to unify that with starting at 6, including 6, and going all the way to positive infinity. So that's how I'm getting this interval notation here, which I hope is adequately represented by the graph. Like there's, I feel like lots of connections between the graph and the interval notation. You are unifying this set over here going from negative infinity, that's coloring in this arrow point here, and going all the way up to 2 and including it, hence the bracket, sorry, negative 2, going all the way up to negative 2 and including that endpoint, and I'm unifying it with this other set starting at negative 6, including it, hence the bracket, and going off to positive infinity. And that's it. Those are all the examples that I have for you in this lecture video. I hope that was helpful. Please let me know if you have any more questions on this stuff in class. See you soon. Bye.